for the lecture. So let's take a quick recap of the last couple of concepts we learned. So the important formulae that we saw, one was refraction at a spherical surface. So whether we are going from denser to rarer medium or rarer to denser, whatever be the case, and whichever side the center of curvature falls in, it doesn't matter. We saw that if this is the pole and we have an object over here, and we have an incident ray, something like this. At the point of incidence, the normal becomes this one, line passing through the center of curvature, and accordingly, wherever it is bending, whether it is bending towards the normal or away from the normal or whatever. So by application of the Snell's law concept along with the paraxial ray, approximation, we saw that we get the formula mu b upon v minus mu a upon u is equal to mu b minus a divided by the radius of curvature with the proper algebraic sign or with the proper Cartesian sign incorporated in this. Okay. And then we saw that when we apply this back to back for two refracting surfaces which are bounding a transparent medium in between, such that the two refractive surfaces are very close to each other. So it's a thin lens. So we saw that this kind of refraction happens twice. Once like this and then once more like this. So if, for example, this is a glass lens with air on either side, we get the standard lens maker's formula. Which tells us that 1 upon focal length of the lens is refractive index of glass with respect to air minus 1 into 1 by R1 minus 1 by R2. And further, we get what is called the lens formula, which gives us a formula to find the position of the image for a point object. 1 by b minus 1 by u is equal to 1 by u. And later today we'll also see about magnification. We'll see what this is. So let's start with some basic examples. So we have a situation like this now. Now this is a very standard type of example. What is called a symmetric biconvex lens. It is made of glass which has refractive index 1.5 and it has a focal length of, let us say, 60 centimeters. So we want to find the radii of curvature of the sides. Both will have the same radius of curvature because it is symmetric. And secondly, if this lens is cut into two plano convex lenses, then find their focal lengths. So if we cut this lens, which is symmetric biconvex like this, if we cut it using a plane which is perpendicular to its principal axis and passing through its pole, so we get, on cutting it, we get two plano convex lenses like this. So if this side and this side each had radius r, now you can see there's a plano-convex lens. So this is the plane side, and this side has a radius r. This is again the plane side, and this side has radius r. So you want to calculate how much will be the focal length of these half lenses or these plano-convex lenses. Just try this out. So I'll just give you a recap of all the formula involved. So for this question, you will not need the first formula. You need these, the lens maker's formula, and in fact, that's all you need. The lens maker's formula. So just try this out. So tell me when you get the answer for the radius of curvature. Yes, I see I have got a couple of answers. Yes, Jatin, your answer is correct. Okay, so Aditya, Siddharth, all of you, it is correct for the radius of curvature. And Siddharth, it is correct for the focal length also of the half lenses. Others, unfortunately, you have got something wrong in the sign convention. So maybe sign convention or application or whatever. So let me work it out. So here, this is the type of application we have to use. So to understand that, if we consider sign convention like this, light coming from this side, then we'll have to consider the first surface is center of curvature here, because this is the first surface. And the second surface is center of curvature here, because this is the second surface that light is. Okay. So accordingly, what will happen is PC1 is equal to PC2 is equal to R, which we have to find out. But we'll have to substitute R1 therefore with sign convention as plus R, and R2 with sign convention as minus R. Because R is just a distance, just a magnitude. So with sign, it becomes like this. So 1 upon F becomes refractive index of glass with respect to air minus 1. 1 upon R1, which becomes plus R, minus 1 upon R2, which becomes minus R. On substituting, you can see that 1 upon plus 60, because we also know that a biconvex lens will give you a real focal point. So the light coming from infinity, it will bend like this. So it's going to give us a positive focal length. So that should become equal to 1.5 minus 1 into 2 by R. So interestingly, this special case gives you the radius of curvature equal to the focal length's magnitude. But that is happening because of two things. Because R1's magnitude is equal to R2, so symmetrical, and also because refractive index of glass is 1.5. Had it been 1.6 or any other value, this will not happen. So you can't take this as a generalization. This only happens in the case of, remember, it happens only in the case of symmetric lenses with glass refractive index exactly equal to 1.5. So that this term outside is 0.5. It's very necessary. That should be 0.5, that mu minus 1. Otherwise, this will not happen. Okay. So that's the thing. Okay, so that's the first part. We got the radius of each part. Now about the second part. Now whether you consider this lens or you consider the other one, it's all going to be the same, because light coming from this side. So you can see here the first surface is this one, and the second surface is this one. So the first surface is center of curvature is here, such that this distance now we know 60 centimeters. We know that from previous, using this value rather than this value. So with that, but we also know that the second surface's radius is tending to infinity. It's a plane surface. So R2 should be tending to infinity. So with this, we know that 1 upon F will become the refractive index of glass with respect to air minus 1 into 1 by R1 minus 1 by R2. It becomes 0.5 by 60 or 1 by 120. That's 1 upon focal length. So let's say this F prime, because this is the focal length of the half. So F prime is 120 centimeters. And it's a converging lens because we are getting it as positive. So that means it's going to send light. It's going to make the parallel beam bend like this. So that this goes and meets over there. And the focal point will be at 120 centimeters. Okay, so note this down, and you can just quickly cross check that if you took the other one, which had the first surface as plane and the second surface as the spherical one, the other half of it, for that also you'll get the same focal length, you get identical focal length, because it's basically the same lens, is just being flipped. Now we discussed last time that when you flip a lens, its focal length does not change. It has that symmetry, that light coming from either side behaves in the same way. Right. So if you take a lens like this now, light coming from this side, for this you will have to consider R1 as infinity, tending to infinity, because it's the plane surface first, and R2 will become minus of 60 centimeters, because the second surface is the second one. Its center of curvature is here on the negative side. So on doing that substitution, you will get the same form. You will get the same value. So this will also behave identically. So that's about lens maker's formula in this equation. Next, let us look at this equation of biconcave lenses. And through that, let's understand the nature of diverging lenses and what we call a virtual focal point or a virtual focus. Let's understand how this works. So if we have some kind of a lens where both the surfaces are concave, they need not be symmetric. So they can have different values of radii, but they are both concave. So let's say this one is having a radius of, let us say, 60 centimeters, and this one is having a radius, let's say 45 centimeters, whatever, something like this. Now we want to find out the focal length and all that. So we consider light incident from this side. And we apply a normal sign convention. This side is negative, this side is positive. Now we can see that this is the first surface it's hitting. This is the first surface. So that one center of curvature is here. And from the pole, it is supposed to be at a distance of 60 centimeters. There's a second surface the light is hitting after this refracted. Its center of curvature is, let's say, somewhere here. The pole to that one, that is 45 centimeters. And let's say it's a normal glass. Yes. So now we can see that lens maker's formula here. That it gives us 1 by f. Now the sign convention. So here when I substitute R1, notice that it will be minus of the distance PC1 because it's on the negative side. So it's minus 60 centimeters. But when I substitute R2, it will be plus PC2 because it's on the right hand side. So it is plus 45 centimeters. So doing that substitution in the formula, now we get 1 upon focal length is 1.5 minus 1 into 1 upon R1, which is this, minus 1 upon R2. So you can see that it doesn't matter what the values of R1 and R2, but the whole thing will always be negative because it's 1 upon a negative quantity minus 1 upon a positive quantity. So it has to be negative, whatever the magnitudes are, whether they're 60, 45 or anything else, it has to be overall a negative quantity. So this, in this case, it becomes 0.5 into, now we can take 90 as the LCM, oh sorry, 180 as the LCM. So this is minus 3 minus. So this becomes the focal length. So the focal length or the inverse of the focal length. So the focal length becomes 360 divided by 7 or approximately minus whatever. So the negative focal length, what it implies? It implies that the lens is a diverging lens. Of focal length (51.4). So coming back to the diagram, what it means that the light here will emerge in such a way that divergent, such that when we produce back these divergent rays, they will give us an image at a virtual focal point. Let's see some value. So this distance level. That is, so this is a, it gives us a virtual focal point, because for an object which is very far away, so typically tending to infinity kind of distance, the image is formed, a virtual image is formed like this. Okay. So an observer from this side will be actually able to see the image of that object at infinity. So if we have an observer who is having normal line of sight, he is able to see a virtual image of the object at infinity with the such that the virtual image is at that virtual focal point. So this is what we mean by diverging lens, and this is what we mean by virtual focal point. So this is the next important application of lens method formula. Last time we had seen biconvex lenses in detail, and we had seen the nature of converging lens in detail from that. Now we see the nature of diverging lens. Okay, now let's see a couple of examples of the application of UV formula in each case. A point object is kept in front of a biconvex lens of focal length 60 centimeters at a distance of x from its pole on the principal axis. Find the position and the nature, that is real or virtual, of its image if x is equal to, in one case, 180 centimeters, another case x is equal to 45 centimeters. Okay. Just try this out. This will give us enough practice to understand the application of the UV formula for lens with proper sign convention. Yes, Aditya, I'll answer that question about the it being placed in a denser medium. But in a normal question like this, when nothing is mentioned about the medium in which the experiment is happening, you have to assume that it's happening in air. So by convex lens made of glass or plastic or whatever, it will always act like a converging lens because it will have a refractive index greater than the refractive index of air. In a specific situation where it is under a liquid or something, and the liquid's density might be such that its refractive index may or may not be greater, then you have to worry about whether your biconvex lens is becoming like a diverging lens. We'll discuss a question or two like that also. But in this kind of situation, you don't have to worry about that. You have to assume it's a normal experiment happening in air. So definitely it will act like a converging lens. So here, if we assume that the object, Ashwin, in the first case, you should get a real image. In the first case, you should be getting a real image. Anyway, so if we assume that this is the principal axis. Now, yes, Siddharth, that's correct. If we assume the object is kept on this side, such that the distance OP is 180 centimeters, then the focal position will be on this side. Because remember, for light coming from here, Biconvex lens gives you a real focal length or a real focal point. So this will be 60 centimeters. So with sign convention now we'll have to use this, that u will be minus 180 centimeters. This side is negative, this side is positive. And v will be positive. Sorry, v we have to find out, of course. And focal length will be positive of 60 centimeters. So 1 by v minus 1 by u is equal to 1 by f. So this formula will give us. But the thing is, don't confuse this formula with the mirror formula. Okay, there it was 1 by v plus 1 by u. Here it's minus 1 by u. So you have to keep that in mind. That the formula across mirror and lens is not. See, v is coming positive. So v is coming positive means it is a real image at the distance OP is equal to 90 centimeters on the right side. The above diagram it will become on the right side. Okay, so hope you understood this application. Okay. Now similarly work out the second part also, and there you see you get virtual. So I'll come back to the ray diagram and show you. Okay. Just give me a moment. Yes, Jatin, I think your answer is correct. So just a moment, people. I'm having unfortunately some internet connectivity issue again. So my whiteboard is rebooting. It's just coming on again. In the meanwhile, try to get the answer for the second part. So in this part, you should be taking u as minus 45. You should be taking v as focal length as plus 60. Yeah, so I've got many people's answers and it appears to be correct. So minus 180 is the value V you should be getting. So it is a virtual image in this case. So try to make a ray diagram now to understand and justify that, how that is coming. Okay? Okay, so I'm almost all set to restart. Oh, so in this case, what we were getting according to the solution, the first case, what we were getting is that rays incident from this, they actually happen to be converging at a point where V was how much? 90, I think, right? That didn't get registered. Okay. So V is plus 90. That gave us a real image. Such that these rays now actually converge somewhere over here to give us the real image at a distance of 90 centimeters. So that was the first part. Now coming back to the second part, we have taken that distance as 45 centimeters. So what is happening here is that the object is actually comparatively closer. Okay. So when you compare, for example, with the focal position here, so these rays they deviate like this. They deviate, bending in a convergent fashion, but they don't converge enough. So if you continue this ray, it's become like this now after refraction. So the refracted rays are diverging actually. So you have to produce them back. The refracted rays have to be produced back to give you the virtual image. At a distance of now, this was 180 centimeters because this was 40 and this was 60. So let's work it out. So here you are putting U as minus 45. You're putting F as plus 60. So V you will get as minus 180. So the moment you get V as minus 180, you know that it is a virtual image because of this kind of thing. Okay. So we'll be doing a thorough analysis of all these things very soon. Okay, now let's see another part of this question. Now, the same question, third part. The glass of the lens has refractive index equal to 3 by 2 or 1.5. Now, find its focal length when placed underwater. So if I take this same glass lens as I had before, but I place it underwater, and it's given to me that refractive index of water is 4 by 3 or 1.33. Now, how much focal length it will have in this kind of situation? Rays that are coming parallel to the principal axis from infinity, how they will behave after refraction. Okay, now you might think over here that there's a bit of problem because I don't know the individual radii of curvature. But the method of solving this is a very standard method, and you can remember it as a basic formula also. In air, for any given lens, 1 upon focal length will be equal to refractive index of glass with respect to air minus 1 into 1 by R1 minus 1 by R2. So take that as your equation 1. Now, when placed underwater, the refractive index becomes, let's say, this. To denote that it's refractive index placed underwater. Or you write it as any other variable, like prime whatever. But this becomes refractive index of glass with respect to water instead of with respect to air minus 1. And nothing else changes. You're not changing the shape and size of the lens. So the radii of curvature are remaining the same. Those are independent of refractive index. So even though I don't know R1 and R2, I can just do this now. I can take equation 1 and divide it by equation 2. I'll get this very standard formula that refractive index of the same lens under water divided by refractive index in glass will be this one. Okay. Now this quantity will become 3 by 2 minus 1. But the quantity in the denominator, refractive index of glass with respect to water, this will actually become 3 by 2 divided by 4 by 3. This thing minus 1. Because here you are using that simple concept that refractive index of A with respect to B is absolute refractive index of A divided by absolute refractive. So glass with respect to water is a refractive index of glass divided by refractive index of water, which is 3 by 2 divided by 4 by 3, which eventually will become 9 by 8. Okay. So this equation now reduces to this. The focal length in water, which is unknown quantity, but focal length in air was 60 centimeters. That will become 3 by 2 minus 1, which is half, divided by in the denominator 9 by 8 minus 1. That becomes 1 by 2 divided by 1 by 8. That becomes 4. So the refractive index underwater, the focal length underwater will just become 4 times the focal length in air, or 240 centimeters. So this is a trick kind of thing that you should know how to do. Okay. Given the focal length of any lens in air, you can calculate the focal length of that lens when placed under some other medium, where you will just replace the term, this one. You will replace the term of focal length of glass with respect to air. This term, you will replace it with focal length of glass with respect to whatever medium here. In this case, it is water. So this is like an additional sort of application of lens maker's formula, which is very important. Okay, people. Now let's see a very interesting special case of this. We have a convex lens of focal length 100 centimeters, let's say, of plastic, transparent plastic, which has refractive index with respect to air of, let us say, 1.2. Now, next what we are doing is, now this lens is placed inside a heavy organic but transparent fluid. Oof. People, you have to give me a second again. Having some internet problems. Just take a minute, okay? I'll sort it out. I have to go and reboot my router, I think. Sorry, guys. Thanks for your patience. Just take a minute off. I'll reboot my router. Okay, so people, unfortunately, I'll have to start that question fresh. But anyway, here it goes. So we had that plastic focal length, plastic lens. It had a focal length of 100 centimeters, and the refractive index of plastic I had taken as 1.2. Now the thing is, I want to place this. So now this lens is placed inside a heavy organic fluid. It is of course transparent, but it has refractive index mu of the liquid, let's say, is 1.4. So find its focal length and comment on whether it is a converging or diverging lens inside the fluid. So this is a thin biconvex plastic lens like this to begin with. And now what we're doing is we are placing it inside a fluid which has refractive index 1.4. The plastic had refractive index 1.2. So we have to find out what its focal length becomes. And on the basis of that, we have to find out whether it acts like a converging lens or a diverging lens. So anybody got the answer for this yet? So you'll see the whole nature of refraction changes, because earlier when you're going from air to plastic, you're going from rarer to denser medium. Ashwin, that is correct. And then when you're going from plastic to air, the second refraction, it's happening from denser to rarer. But inside that liquid, that whole sequence of events has become like an inversion. Okay. So you will see here that in air, this lens very much behaves like a converging lens. If we have light coming from this side, we understand it's acting like a converging lens. Why? Because we can see that in this, when we substitute with sign convention, R1 will be a positive quantity, R2 will be a negative quantity. Therefore, 1 by F, which is refractive index of plastic minus 1, into 1 by R1 plus 1 by R2, it has to be positive. Which means that in air, it has to be a converging lens. So we will understand that in this formula, in equation 1, the value of F is plus 100. Even though the question is not giving us that directly, the question has only said that it's a biconvex lens. But since the refractive index of plastic has to be greater than 1, there's no option, and it's given also, and air is unity, so we understand that It has to be a converging lens. Yes, lovely, that is correct, good. Okay. But the same thing when we place it inside the fluid now, so this is plastic having refractive index 1.2, but it is in this fluid now, let us say like this, which is having refractive index, sorry, refractive index of the liquid that is equal to 1.4. Okay. But the R1 and R2 are the same from above. This side is having R1, which is a positive quantity. This side is having R2, which is that negative quantity. And we are considering for focal length calculation, we are considering light coming like this only. So here if we calculate the focal length using the lens maker's formula now, 1 upon focal length, but inside the fluid, it becomes refractive index of plastic with respect to the fluid minus 1 into 1 by R1 minus 1 by R2. So this becomes the second formula. So if we now compare the two formulae, equation 1 divided by equation 2, because focal length in the liquid divided by focal length in the normal situation is refractive index of plastic minus 1 divided by refractive index of plastic with respect to the liquid minus 1. So here when we substitute this quantity with our sign convention, it is plus 100, and this quantity is 1.2 minus 1. But this quantity here actually becomes 1.2 divided by 1.4 minus 1. So interestingly, here you can see the focal length becomes plus 100 multiplied by 0.2 divided by minus of 0.2 by 1.4. So it becomes 100 into minus 1.4. Becomes like this. So the focal length has become negative, means that it's now behaving like a diverging lens. Okay. So this implies that inside the fluid with refractive index 1.4, in fact, the biconvex plastic lens acts as a diverging lens of focal length 140 centimeters. So why it acts like a diverging lens in spite of being biconvex? Why it acts like a diverging lens is because actually that is happening because this term refractive index of plastic with respect to the liquid is less than 1. That's why it is happening. This term is actually 1.2 divided by 1.4, so it's less than 1. So that is why the nature of the lens is inverting. So what normally behaves like a converging lens, in this extreme circumstances, it is acting like a diverging lens. Okay. So back in this diagram, what will happen is this light will now actually come out diverging lens. So it's not that suddenly it's become a biconcave lens. It's a convex lens only because the geometry has not changed. But what has changed is the behavior of the light, how it is behaving in each of these refractions. Because instead of going from a lighter medium like air to a denser medium like plastic, it is now going from a denser medium like that liquid into plastic, then from plastic into a denser medium. So I'll just minimize this, but I'm sure the calculation is pretty clear to all of you. Right, I'll just put up the equations 1 and 2 first. So the above one, equation 1 is the normal situation in air. Okay, this is a very interesting but very extreme kind of situation. Okay, as you can see, one doesn't expect it to happen in normal everyday circumstances, but this is how it behaves when this happens. Okay. Okay, now let us move on a little bit towards another type of lens. So we've already seen that plano-convex is converging, biconvex is converging, biconcave is diverging. But what about these type of lenses? Concavo-convex lenses. Let us understand their nature. So typical concavo-convex lens will look something like this. It has a concave side and then it has also got a convex side. Now you can see here that if we consider this one, okay. Now suppose this has refractive index of glass as 1.5 and the radii are just randomly given to me as, let's say, 60 centimeters and 90 centimeters. And I want to find the focal length. Now we have to understand which one is which. Okay, so when we consider light coming from this side, parallel light coming from infinity, we have to understand here that it hits this surface first. So this will become our first surface of refraction and is going to hit this surface after that. So this is our second surface. So as it hits the first surface, if you just look at the first surface, it is a part of, it's a part of a circle which is like this now. The first surface is a part of a sphere which is like this. So its center of curvature is somewhere here. But if you look at the second surface, it is part of a much smaller radius. Let's say something like this. This surface is part of a sphere like this. So its center of curvature is here. So coming back to this, you can see that it is the first surface which will be having the larger radius over here. Even though I've given the radius in ulta order, 60 and 90. But I didn't say that this one is 60 and that one is 90. So that you have to figure out from the geometry of the diagram. Okay? So what I'm saying is that every time a concavo-convex lens is given, just understand that the concave side will always have a larger radius of curvature compared to the convex side. It will always be the case. So I'm just drawing them with different colors so that we understand that. It's like this. This one is part of this surface. Okay. And the earlier one is part of this kind of surface. So overall, what will happen for this lens? Always this surface that I have over here, the concave side, it will have larger radius. And the convex side will have the smaller radius. So that is why the moment the radii are given to you as 60 and 90 or whatever values they are given, you should understand which will be the one having the larger radius. It will be the concave side. And which will be the one having the smaller radius. It will be that. Okay, so here you can see that PC1 will be equal to 90 centimeters. So I will have to take R1 with my proper sign convention as minus 90. And PC2 will be equal to 60 centimeters. So R2 will have to be minus 60 centimeters. So hope this point is clear to all of you. So now with these, when you substitute in the lens maker's formula, so 1 upon F is equal to mu of glass with respect to air minus 1. 1 by R1 minus 1 by R2. So there, if you go back, my R1 was the concave surface, so it was the larger side, so it was minus 90. And R2 was the convex side, so it was the smaller, so it was minus 60. So now if you substitute, you will see you will get the focal length always as a positive quantity. Because remember, R1 is negative, but its magnitude is more. So it is like, so even if this was not 90 and it was 180 or 120 or anything like that, but still you will see that you will always get a positive quantity for light coming from this side, which means that it behaves like a converging lens. So this is 0.5 into 1 by 60 minus 1 by 90, which is 0.5 into P minus 1 by, sorry, P minus 2 by 180. That is showing you that the focal length is positive. It is positive of 360 centimeters. That means it acts like a converging lens. Okay. So unless you have that extreme circumstance where it is in a liquid which is denser, that don't worry about that. That's a special case. Normally we're talking about air. So what will happen is this kind of lens will always end up causing this kind of refraction. Light coming out from this side will converge. Give you a real focal point. Okay, so that is the example here, but that is also what we take away from the example in terms of our learning, that a concavo-convex lens, first of all, you have to understand it is the concave side which will have the larger radius and the convex side which will have the smaller radius. So when you put that into the formula with proper sign convention, you can see it doesn't matter ki R1 or R2 ki values kitne hai, whether they are 120 and 90 or 90 and 80 or even very close to each other like 10 and 11, whatever be the case. But the focal length will always be such that it shows you it is a converging lens. So ultimately what we learn from here is that biconvex, plano-convex and concavo-convex, all these always act like converging lenses. But remember, I am saying converging in context of the normal situation when it is in air. You put it in a denser fluid, it becomes a different matter. Whereas biconcave and also plano-concave, under normal circumstances in air or a lighter medium, they always act like diverging lenses. No exceptions, other than the fact that if you change the medium around to a denser medium. Apart from that, there are no exceptions to this. Okay. So I'm just going to take you through this systematically. So this is our example of concavo-convex lens. So I know it will be 5:30 by the time we finish, but just make sure that you do a revision of today's lecture and the last lecture, the 4th lecture and the 5th lecture. If you do a revision of all the examples we have done in class, then you will be in a pretty good position for tomorrow's test. So the important thing to remember about the shape of the concavo-convex lens, that's what I've shown over here below. There's always a concave side which is having the larger magnitude radius and the convex side which is having the smaller magnitude radius. So that is why you see that when you substitute this information in the formula like this, ये 90 or 60 but जो भी values होते हैं यहाँ पे this will always 1 by f will always come out to be a positive quantity. Okay, so diverging and converging lenses. Now, next thing in our analysis we'll see is magnification and extended objects, how to consider that. For that, it's a very similar kind of analysis to what we had done for mirrors. So first we'll understand the general principles of ray tracing. So if we take the example of a converging lens, so it could be plano-convex, it could be biconvex, or it even could be concavo-convex. But the important thing is it is converging. So for light coming from the left side, the focal position will be on the right side, be a real focal point. So this is my principal axis. So I'm considering light coming from the left hand side. So any beam that is parallel to the principal axis, after refraction it passes through a particular point, and that point is what we call the focal point. That is the first type of ray that we should consider. And the second type of ray is like the reverse of this, if you apply that principle, that a ray which is aimed at the focal point. You just apply reversibility here. This after refraction becomes parallel to the principal axis. So this is reversibility applied on the first one. If you make this the incident ray, oh, sorry, wait a minute, this is not correct. I have to make an adjustment in the diagram. Yes, so the second one is actually like this. If we consider a ray which is coming from the focal point, passing through the focal point, then after refraction, parallel to the principal axis. So this point here will become the focal point's image on this side. So this ray after refraction will become that. And the third type of ray that is worthwhile for us is this one. The ray that passes through the pole, it goes undeviated. As long as we are talking about a thin lens. For a moment, I'll show you why that happens also. But just make a brief note of this first. Okay, so to understand what is happening to the ray which is incident at the pole, you have to first think like this, that if I have a glass slab, then what happens is a ray of light which is incident like this on it. Instead of this, it emerges out like this. Inside, first bends like this, and then again comes out parallel. So it emerges out more or less parallel to where it came from. So it does not have any angular deviation. It just has a lateral deviation. When you consider a slab, this is what happens. So this lateral deviation delta x is actually proportional to this thickness of the slab. Delta x is proportional to the thickness T. So if the thickness is tending to 0, this is tending to 0. So there is no deviation. So there is no deviation whatsoever. Neither angular deviation nor lateral deviation. So now that is how we'll consider the middle portion of the lens where the pole is present. The middle portion of the lens where the pole is present is like a very thin slab. So it becomes like this. So that is why a ray of light that is incident here should technically come out with a little bit of deviation from this, like this. It should come out like this, but no, because we are considering the thickness is negligible, we will consider it comes out undeviated. Undeviated. So that is the logic of why the ray incident at the pole comes out without any deviation. Alright, now similarly, when we consider an extended object for a converging lens, now suppose for our converging lens, the focal length on this side, I mean light is coming from the left hand side, so the focal point is over here, somewhere here. Let's see. This is the focal point, this is the pole, and we have kept a sort of extended object somewhere over here. In fact, let's consider the pole to be, sorry, the focal point to be a little bit closer. Be easier to draw the diagram. Suppose the focal point is here, whereas this is where my object, extended object EB is. Now to understand where the image of the tip B is formed, consider any two light rays which are incident from B onto the lens. So first I'll consider the easiest one, the one which is parallel to the principal axis. That will pass through the focal point after refraction. So this ray will go like this. Next I will consider a ray which is just passing through the pole. So that one will go undeviated. So consider a ray from that same tip B, but it's just going through the pole. It's going undeviated like this. And now, for example, if you were to also consider a ray that is passing through the focal point on this side, it would become parallel to the principal axis after refraction. So that sort of a ray would look like something like this. The ray that is emerging out parallel to the principal axis, that must be the ray that is such that it passes through the focal length distance point, or the image of the focal point on this side, f prime, let's say. This must be a ray of light, something like this. So all such paraxial rays you will see will intersect. So any rays coming out of the tip point B, after refraction they converge in such a way that they converge to this point here. So that becomes the image of that. So like that, all other points also we consider. You see this becomes this. Okay. So you can see that this is an example of a real and inverted image. Okay. Now the key here again is that the ray which is passing through the pole is undeviated. Therefore, this angle is equal to this angle because it is undeviated. So if this angle is theta, here this angle is also theta. So keeping that, we get the same kind of analysis that we saw for mirrors. You'll see that triangle. So triangle ABP and A prime B prime P are similar triangles. So AP upon AB will become on the other side A prime P upon A prime P. Or in other words, the height of the image divided by the height of the object is nothing but the image distance divided by the object distance. So we can call this as the magnitude of magnification. And that is magnitude of V divided by magnitude of V. Now we can see over here, in this case, V is negative. V is positive, my mistake. It's on the real side. U is negative. And it's an inverted image. So the inverted image implies that the magnification should be taken as a negative quantity. The algebraic sign of magnification should be negative. So you can see that with the algebraic sign, M just becomes V by U. In mirrors, it was minus of V by U. In lens, we'll see, not only in this case, but in all cases in lens, it becomes V by U. So the formula for magnification becomes V by U. Okay, people. So hope this part is clear. So make a quick note of this, and we will show that very similar derivation for this thing also, for the diverging lens also. And before that, we'll also show that a converging lens, remember, can also give you a virtual image, which we've discussed in that example earlier. So in case it's a virtual image, even then the magnification is given by the same formula. Okay, people, so hope this is clear. Right. So now let us look at the situation where we can get a virtual image from a converging lens also. So for that to happen, we have to keep the object somewhat closer. It has to be at a position where the distance of the object is actually becoming less than the focal length of the lens. If we do that, you'll see that that is what tends to happen. So if, let us say, this is the focal position, this is the pole. So on this side, this is the image of the focal position. Now suppose our extended object just a moment. Yeah. So suppose just our extended object is here now. It's like this. Then a ray which is parallel to the principal axis, that's the easiest one to start with. That will, after refraction, pass through the pole, pass through the focal point. It goes like this. So over here, that's, now we need a minimum of 2 rays to understand the position of the image. Now let's take the other one as a very easy one, which is the one passing through the pole. That goes undeviated. So this ray now you can see. So you can see that even though it is a converging lens in general, these 2 rays which are refracted, they are not converging in nature, they are diverging. So they are not going to give you a real image. In fact, you will have to produce them back to get the virtual image. So what we have to do next is we have to produce this ray back. So let's say that's something like this. And we have to also produce this ray back. So let's say that's like this. So now you can see that when you are observing from the other side, it is really that what's happening is that an observer on this side now is receiving these kind of rays which are diverging in nature. So they never form a real image which can be collected on a photographic plate. But these rays appear to be coming from a point behind. And that is a virtual, and in this case you can see it is an upright image. Okay, so you can see it is a virtual upright. And in this case we can also very clearly see that it is magnified. It's larger in size. That kind of an image. And again we can see that triangle ABP and triangle A prime B prime P, they are similar. So by that same logic, that AB upon AP is equal to E prime B prime upon E prime P, you will get that the size of the image divided by the size of the object is nothing but the image distance divided by the object distance. So you get the magnitude of magnification is magnitude of V divided by magnitude of U. Now this time when you incorporate the sign convention, you can see that it is an upright image. Therefore magnification should be positive and V is negative and U is also negative. So with the sign convention, the formula of magnification remains V by U. So whether we have the case of the virtual image production or the real image production, we can see that the magnification formula remains V by U. Okay. So we can make a quick note of that, and then we come to the diverging lens, and I'll show you that there also the formula for magnification is the same. Okay, people, so hope this is clear. Now let's come to the case of diverging lens. Understand the ray tracing and extended objects. Diverging lenses. So in this case, they have to be biconcave or plano-concave. Cannot be concave or convex. Okay, so first of all, as far as the ray tracing is concerned, the rays we have to consider are these ones. First of all, any ray parallel to the principal axis. After refraction, it emerges out such that it appears to be coming from the focal point. So now if I apply reversibility to this one, we will get the situation that any ray that, for example, appears to be incident on this point f prime, which is the image of the focus on the other side, such a ray after refraction will become parallel to the principal axis. This kind of a ray becomes parallel to the principal axis after refraction. And the third is the very, very simple one, the one which is passing through the pole. It was undeviated. Okay, so these are the three standard type of rays that we can use as guidelines for solving ray diagrams. Okay. Now what we do next is use this and make a diagram for an extended object kept anywhere in front of the lens. And you will see that you will get a virtual image. I'm coming to that, but just make a note of this and start working on the next diagram, which is this one. So I mean, briefly, the next diagram that we're going to work on here is like this, that in front of this lens, at any given distance, you keep an extended object AB and you work out where the image will be formed using these guidelines which I've shown. You will see that you will get virtual in all situations, and it will be a very specific type of virtual image. Yeah, to answer your question, Peter, it is up to lenses. I mean, thin lenses. In the test coming up tomorrow, it is up to thin lenses analysis. So spherical mirrors, thin lenses, okay, critical angle, refraction at plane surface, refraction due to a slab, that lateral shift due to a slab, that formula, thickness into 1 minus 1 by mu, all these things. What is not going to come in test is about dispersion from thin prisms and this thing, optical instruments, which is telescope, microscope, etc. And also combination of lenses, which we will be seeing in the next lecture. These things will not be coming. Yes, very good, Manishka. You will get a virtual but diminished upright image. And you will also notice something, that that image is always between F and P. It will always be between the virtual focal point and the pole. So you get an image in a very restricted region. Just like that for convex mirrors, very similar, but there it was the virtual image behind the mirror. Here it is the virtual image in front of the lens. So you'll see any sort of object that we give. By any sort, I mean irrespective of where the object is in relation to the focal point. So the focal point is here, for example. Now consider an extended object kept over here. On this side of the focal point. So here, consider an incident beam like this now, parallel to the principal axis. So after deviation, goes something like this. Now also consider the second one, which is very simple, the ray passing through the pole. Just any two are enough, so we'll consider the easiest one, which are this. This goes undeviated. So you see the observer on this side is receiving this and this. So these appear to be coming from which point? They appear to be coming from this point over here. So the virtual image becomes this. So this was my extended object AB. You can see you are getting a virtual upright and diminished image. Like this. And that will always be, it is between focal point and pole withaut fill. It will always be between the virtual focal point and pole. I'll show you, even if the object AB comes a lot in front, even then it will be that way. Even then it will be diminished. And it will be in between the focal point and pole. Now for your magnification analysis, you can again see that triangle ABP and triangle A prime B prime P. So if you follow all that, you'll get again magnification with proper sign convention is still V by U. So that is why the formula for magnification V by U is universal for thin lens, whether it is converging lens or diverging lens. And similarly, the formula of magnification for mirror is universal. It is minus V by U. Yes, these concepts are included better because this is like application of lens maker's formula and analysis of thin lenses. So what all we had derived in the last lecture, it's all analysis is part of it, which is today's lecture. But having said that, most of the focus in the test for your, for tomorrow's test will be more up to lens maker's formula. The focus will be more up to lens maker's formula, which was last time's lecture. So the area that you should really focus on is the spherical mirrors, the refraction at plane surface, the refraction due to thin slab, and the lens maker's formula application itself. So if you just revise the first few questions we've done in class today, that cutting of the lens by convexo-concave lens, etc., that is the important part from today's lecture. Whereas lectures 3 and 4 are very important. Critical angle, total internal reflection, spherical mirrors, normal incidence at spherical mirrors causing retracing of rays and all that. Okay, so I will just quickly take you through another type of ray diagram, which is also very interesting. So if we have an extended object now, which is the extended object happens to be even closer. Yes, like this. Initially, we might think that such an object, how can it give us a diminished virtual image, and that too between f and p. But if you just follow the ray diagram, and of course, to get the value, you can always use the Lenss formula. Okay. So we'll do this with an example also. Suppose in the example, the focal length of the lens is, let us say, 60 centimeters, and the object distance AP is given to me as, let's say, whatever, 45 centimeters. We have to find the position of the image and all this. Position and nature of the image. We are done like this for convex lens, but now we are doing for concave lens. Okay, so we'll see with proper sign convention. But first, let's follow the ray diagram. So according to the ray diagram here, what is happening is that a ray parallel to the principal axis, it will now, after reflection, take this kind of a path. It appears to be coming from the focal point. So it diverges such that it appears to be coming from the focal. This is our first ray. And our second ray is the very easy one, the one passing through the pole. That goes undeviated. You can see that again the image is in front. Again the image will become such that these are your two refracted rays, so they are diverging. So you are having to produce them back, and they appear to be coming from this point over here. These two rays, this coming out like this and this coming out like this. Where do they appear to be coming from? So for that you produce this back. They appear to be coming from this point. So that point over there becomes the image of the point B. So you're still getting that same thing. So you always get virtual, diminished, and upright. Image between F and P. Now let's check this with the values. Okay. Let's check. So here with the sign convention, the focal length should be minus 60 centimeters because it's a virtual focus. The object distance with the sign convention should be minus 45 centimeters. So 1 by V minus 1 by U is equal to 1 by F. When you substitute, okay. So you can see it is becoming minus of 1 by 60 plus 1 by 40. It is becoming minus of 3 plus 4 by 1. So V is equal to minus of 180 by 7, or approximately minus of something like this. Okay, and the magnification, which is V by U, is minus 180 by 7 divided by minus 45. So that is becoming positive of so we can work this out, but this will be a positive quantity which is less than 1. So it will show you that it is diminished. So I'll complete the calculation, but you can see how with the proper sign convention, when you substitute, the calculation agrees with the diagram that we've drawn above. So it's simply 4 by 7. The magnification is simply positive of 4 by 7. So it's a diminished image, but which is upright. and you can see the distance is 25.7 centimeters in front of the pole. That's how this calculation you can see is in agreement with the diagram that we predicted earlier. Now in this diagram also you can see you can prove the magnification formula by the same way. Triangle ABP and A prime B prime P. If you work out all those steps, you will come to the same thing, that magnification will be V by U. So basically anything to do with the lens, the calculation part is by these two formulae, that 1 by V minus 1 by U is equal to 1 by F, and magnification is equal to V by U. You have to just be careful about substituting everything with a proper sign. Because remember, the formula is without sign. And remember, whatever is given in the question to you will be without sign. It's just the distances which are given to you, or just the geometrical factors are given. You have to incorporate the sign yourself according to your sign convention. So the sign convention we are following here is the Cartesian sign convention. So that's how we substitute. Okay, so with this, we have more or less done about lenses. So next up, we'll just be practicing some questions, which will help you out with, being perfect in all of this. But before that, we should understand the various types of images. So just additionally, we should understand here that for converging lens, what happens is, if you keep an object which is at a comparatively larger distance, so the magnitude of U is greater than twice the focal length. So if this is, that image of the focal point, and this is double of that, and this is focal length, this is 2f, then always you get an image which is like this. So when this happens, you get a real inverted, diminished image, which is between f and 2f. Of course, if your u is infinity, then obviously you know that the image is equal to at the focal position. But if the object has come from infinity a little bit closer, so it's now still beyond 2f, but it's closer than infinity, then the image goes beyond f on the other side and it goes towards 2f. It will be somewhere in between. And in that case, it will always be a diminished image. So this is the first type of situation. Now, similarly, the second situation you should know is basically reversal of rays for this one. If you make this the object, then this will become the image. So that is now like this, that if we keep the object between a distance of twice of the focal length and the focal length, then the image on the other side actually becomes, this time it becomes magnified and it goes beyond 2f. So we keep the object somewhere here, we'll see that this time the image form will be somewhere here, and it will be magnified in comparison. And all this you can verify with actual values and all that, or you can verify with a ray diagram. Take two of the standard rays. So if the object is between 2f prime and f prime, or in other words, you can say that the magnitude of the object distance is in between focal length and twice of the focal length. All this without signs, then the image, then we get a real inverted and magnified image. Okay, which is beyond 2f on this side. So you don't have to really memorize these cases, but if you just go through them once, then while you are actually doing numerical problems, the whole understanding becomes much easier for you. And chances of making a mistake with the formula and also becomes less. So for each of these, you can work out an example later when you're revising. So here, for example, you can take the distance EP as, let us say, 90 centimeters, whereas the focal length is only, let us say, the magnitude of focal length is only, let us say, 30 centimeters. So you'll get this case. In this case, so you find out V and you verify this. In this case, you take EP as where P is the pole in both the cases. So here you take AP as a smaller distance, like take it as something like, let's say, 50 centimeters, and the focal length is still 30 centimeters. So you can see it is greater than focal length but less than 2 times the focal length. So you find out the position of image and justify this. You also find out the magnification factor in this. So you'll see it will be a negative quantity, but its magnitude will be less than 1. It will be diminished and inverted. Here it will be magnified and inverted, because M will be something which is negative, but its magnitude is more than 1. Okay. But in between also there is an interesting case, which also you should note down. If the object is at 2f prime, that is magnitude of u is equal to 2f, then we get on the other side, we get something very interesting. We get image at 2f. So we get a real inverted same size image. Or with proper sign, we'll say magnification factor becomes -1, because it is inverted, but it's of same size. So it's 1, but with the algebraic sign of minus. So that's a very interesting special case also, that if the object distance is exactly twice of the focal length, then the image distance is on the other side is also twice of the focal length, but it is a inverted image of the same size. It's a real inverted image of the same size. And now the final case is when, which you've already seen also in a couple of examples, that if the object is between the pole and focal point, then the image is virtual, upright, and magnified. It cannot be diminished in the case of converging lens. Remember, all this we are discussing for converging lens. Diverging lens has only one kind of case. I will come back to that. We've already discussed also. So we keep an object anywhere over here beyond the focal. We keep an object anywhere here between the focal point and pole. You will see that the rays behave in such a way that when you produce these back, they give you somewhere an image like this. It is always this case. Whereas in the case of diverging lens, it is always diminished and upright. Here it is always magnified and upright. Okay? So an important thing to remember is that a diverging lens cannot give you a virtual magnified image. It can only give you virtual diminished image. Similarly, a converging lens or a biconvex lens or something like that cannot give you a virtual diminished image. If it is giving you a virtual image, it has to be magnified. Whereas if it's giving you a real image, it can be either magnified or diminished, like we've seen the last two cases. Okay. So just winding this part up, the final thing. A diverging lens always produce a diminished virtual and upright image between pole and focal point. You can refer to the examples above. We've done examples above. Okay, so you'll understand. So this is the entire thing about lenses. Okay. Now let us see a couple of more typical type of questions. Yes, so see, we have this case here where this is a convex lens of focal length 60 centimeters, and we have a plane mirror kept such that they have a common symmetry axis. Now, this distance between them, between the pole of the convex lens and this one, this distance is, let us say, 75 centimeters. Okay. And now we keep an object, a source of light kind of thing over here at x distance. So we want to find the position of image if x is equal to, let us say, 70 centimeters, and find x such that the final image is at the source. Just a minute, let us change this from 75 to something else. Be a little easier to calculate. That. So 90 centimeters. In the first case, I'm taking that distance x as 90 centimeters. Second case, I'm keeping the distance x unknown, but I'm finding it x for the condition so that the final image coincides with the original source. Just try this out, people. This will be a good practice question, for the application of lenses. so anybody got the answer for the first part? So we'll realize here that light rays, starting from this, they tend to converge like this, but they will not be allowed to converge. When you put the values, you'll see. If this is my I1, so the first refraction is giving you 105, is it? So let's see. So part 1, X is 90 centimeters. Focal length of the lens was 60 centimeters. So let's understand what's happening here. So 1 by B minus 1 by U is equal to 1 by F. So V is coming out to be plus 180. So if it is coming out to be plus 180, you can see that it's never reaching this stage. In between there is a mirror. This is your image from the first refraction. But that is becoming the object for this one. So now what will happen is that this will become like a virtual object for the mirror. So this distance is, let's say, some y. So now for the mirror, what is happening? So this is the for the lens. Now what is happening? These refracted rays from the lens, they are reaching the mirror. So for the mirror, this is the situation. So these will get reflected. This is the case of virtual object, as we discussed earlier. So this is your second image, which is formed by the mirror. So this will be at y distance in front. So for the mirror, the object is I1. So it is a virtual object at y equal to 105 centimeters behind. Okay. So this kind of virtual object will give what kind of image? It's a plane mirror. So the image I2, this will become a real image at y equal to 105 centimeters in front of the mirror. But again, you will see another third refraction also that happens. So light doesn't end over here for it. There is yet another complication that happens, and that is going to be that light reflected by the mirror is again going to be incident on the lens. So there's going to be double refraction by the lens, and that will give us the final solution that we're looking for. But first note down up to here, then we'll see. So you can see the distance between the lens and mirror is only 75 now, whereas the mirror is trying to form an image in front of it at 105. So those rays never reach that image point I2 actually. There's again the lens in between. Okay, so people, as you can see now, there is an added complication in this. We have to still, but is it clear up to this? From the plane mirror 105, it's clear. Aditya, I'll just check your answer. It seems to be correct. But you do now tell me where the image is, to the right or left. So now what is happening? There is a third event also. There is again refraction by the lens. What is happening in the second refraction by the lens is that these rays of light, which were getting reflected by the mirror like this, they are not allowed to reach their image point I2 because they are once again having to go through the lens as our lens. So they are incident on the lens, which had a focal length of how much was it? 60. Yeah, focal length of 60, and this distance was 75. And if we were to produce the incident rays on the lens or the reflected ray by the mirrors backwards, they would have converged here at this point I2, where this total distance would have been 105. That is what we calculated just before this. We got that from here. So that means what is this distance becoming now? It is becoming 105 minus 75, so that is 40. 30. Okay. So now you can see that I2 is becoming like again a virtual object for the lens. Now for the lens, what will happen is when light is coming from this side, for light coming from this side, the focal position of the lens is here. It's not here. So the focal position is here at a distance of 60 centimeters. So we will keep the sign convention the same. We will keep this side as negative, this side as positive. But because now light is coming from right to left, our focal length of the lens will become minus 60. The object distance will be minus of where these two converge. So minus of I1P wala distance, which was minus 30 centimeters. And now we'll find the position of the final image. Now this will become the final image. Whatever we are calculating now, just a moment, yes. I will reshare the screen. Yeah. So this will become the final image. So we want to find that out. Okay. So that's pertaining to this diagram. So what we will see is the final image will now come out somewhere like this. These rays will converge even further. Impossible to draw like this, so I'll just do a rough drawing. These rays will further converge as they come out from here and give you a final image somewhere here. This is going to be the final one. Okay. So this is what the lens is ending up doing. If you see, the lens is ending up doing this thing over here. On the lens, we had some rays coming in like this, and now those rays will converge further and give you this image I3. Whereas this produced forward and this produced forward was I2. So this was the virtual object, and this will be the final real image. So again, use this data here to substitute in the lens because in the UV formula. This is the object for the lens this time. It's of course a virtual object, and this one will become the image, and that's the final image. So 1 by V minus 1 by U is equal to 1 by F. Like this. So the image finally will be at minus 20 centimeters. So the final image, this is the position of I3 with respect to the pole of the lens. So this is where my final image will be formed. So I'll take you through the whole ray diagram once more, but this is how you understand this. Okay. So while you don't need to worry about something so lengthy in tomorrow's exam, but at JEE advanced level, proper analysis of lenses will include these kind of situations where even for the lens you have to consider virtual object. For mirror virtual objects, we have seen number of cases by now. So now just to take you through the entire series of events so that you understand in sequence what is happening here. So we have this lens. Just a moment, guys. I have to refresh software once more. Right. So what is happening here is light from this is first converted by the lens to give you the first image which was behind the mirror, but that image was becoming the virtual object for the mirror. So the mirror ended up reflecting this back like this. And this, if you continue it for further, it would give you I2, but this after coming out from here is giving you the final image here. And I2 is single. So the final image is this one. And as you can see, it's a real image because it is formed by actual intersection. Okay, so it is at 20 centimeters from the pole. So this is what ends up happening. So this is the complete solution of this part. Now the second part where I asked you for retracing of the rays, that's actually very easy. I'll just show it to you, but first make sure you understood this. Okay. So I'll try to get the whiteboard notes up to you within a few minutes just now, so you can do some revision today. But again, I'm saying that this much lengthy question you don't expect tomorrow. Not to do with lenses. Okay, whatever lengthy questions will come, that has to do with refracting slabs and mirrors and things that you've done in fourth lecture and before that in third lecture. In today's lecture, the more important thing is the application of lens maker's formula, how to find the focal length for given radius of curvature for different type of lenses, those kind of things. Okay. Now the second part of the question is we want to find out x such that the final image is at the source. So we want this kind of situation now. Okay. So we want that the rays from the source that go like this, they should retrace and come back. So that means when they go here, they should retrace their path. So that will only happen when there is normal incidence. A normal incidence for a plane mirror means that the ray should be parallel to the principal axis. That means what should happen? The lens should refract such that the rays emerge parallel to the axis. In other words, the image should be at infinity. That means the object should be at the focal position. So how much we should keep x as 60 centimeters. The moment we keep the object at the focal position of the lens, so the moment we keep it at the focal position of the lens, the rays that are coming out, there's some kind of software error happening, so don't mind these other arrows in between. But the moment the source is kept at the focal position, the rays that emerge from the convex lens will be parallel to the principal axis. So they will hit the mirror normally. So they will simply retrace their path, and the rest again they'll retrace their path. So the source will be the position of the final image. So this is the more the JEE mains type of question where not too much calculation is required, just the analysis has to be clear. Right. So this will become your solution for the second part. X should be equal to 60 centimeters or focal length of the lens. That ensures that there is normal incidence at the plane mirror. Right, people. So with this, we conclude today's lecture. So I have to get you the whiteboard notes within half an hour. It takes a little bit of time for the printer. The printer software, to convert it and all that to PDF and all that. So anyway, I'll begin. And as I said, the more important part for tomorrow's test is spherical mirrors and refraction at plane surface, and just simple application of lens maker's formula. So make sure you do that much. So that's it for today's lecture, people. All the very best for tomorrow. And see you next week. Whatever doubts you have in between, please continue to send me the doubts by WhatsApp, etc. I'll help you out with the questions. Some of you have sent doubts which I have answered, some I haven't managed yet, but I will try to finish everything by tonight. Any pending doubts I have on WhatsApp, I'll try to finish them by tonight. Okay. So that's it. Thank you guys. All the best again for tomorrow.